The great Earth cycles of water and air, the subject of the last two lectures, feature rapid changes of material from one repository to another. These changes can take place in days, sometimes in only hours. It's easy to see how the sun powers these systems. It's also easy to see how human intervention can change the systems of water and the systems of air. The rock scale, however, operates on vastly longer time frames, so that rocks reveal the complex history of Earth's landforms and its life. In this lecture, you'll meet the three major classes of rocks: the igneous rocks, the sedimentary rocks, and the metamorphic rocks. We'll examine how these materials continuously cycle Earth's atoms from one reservoir to another. Then I'm going to tell you some of my favorite stories about the epic journey undertaken by some of my favorite specimens of rock. The basic principles of the rock cycle are exactly the same as other cycles of water and atmosphere that we've considered. We know that matter moves from one reservoir to another. We know that these motions have to be driven by energy. We see that the rock cycle is interconnected with other cycles, such as the water cycle and the atmospheric cycle, as well as human activities. Oh, by the way, you might want to consider and check out the teaching company's course on energy and climate, which considers that climate and the atmospheric cycle in more detail. That was given by Professor Richard Wolfson of Middlebury College. Now, the Earth is a physical system. It has a long, complex, and largely unknowable history. That history conformed to all the physical, all the chemical laws that we've considered, but it was influenced by countless random events, unpredictable events that we cannot know in retrospect. The best opportunity to know the Earth lies in studies of the rocks, and that's the study called geology. When studying geology, you're studying the rock cycle. That includes the formation, the alteration, and the destruction of the solid portions of the Earth's crust. It's epic in both terms of time and in terms of scale. Rocks include almost all the materials that make up what we call the solid Earth. If you look at most rocks carefully, you'll see that they're composed of interlocking grains of several different minerals, of different chemical compounds of specific composition and structure. Those are the mineral grains that make up these rocks. So if you pick up a typical rock or perhaps a handful of sand, you're going to see light grains, you're going to see dark colored grains, sometimes you'll see colored ones. Each grain is a mineral, and the uniform compound with well-defined composition and well-defined structure makes up the catalog of some 3,000 different known minerals. But in all the rocks you're likely to pick up, there are only about 50 common rock-forming minerals. If you look at a typical rock specimen, then you'll see some of these grains. Some of them will be colored, some of them will be colorless. You'll see reddish feldspars, you'll see colorless quartz, maybe some dark-colored minerals like hornblende or pyroxene. Quartz is the common mineral that makes up beach sand. It also makes up power crystals, if you've ever worn one of those. It's composed of silicon dioxide, which is the principal chemical element in most glass. If you look at Pikes Peak granite, for example, a granite which I was able to collect right at the summit of the mountain, you'll see colorless grains of Pikes Peak quartz. The commonest crustal mineral by far is feldspar. This is an oxide of silicon, but it also has aluminum, sodium, and calcium. A geology professor once told me that if I was ever quizzed on what minerals might occur in a particular hand specimen if I was handed it, I should automatically say feldspar, and most of the time I'd be right. Again, in Pikes Peak granite, feldspar makes up the reddish minerals that occupy most of the granite. You also invariably have a few dark grains, and these are typically iron-bearing minerals, denser minerals that are often black. In Pikes Peak granite, there are a few black grains of a mineral called amphibole. Now, these individual grains form an interlocking mass of crystals to make the solid rock. Indeed, this interlocking mass is so strong that when you break most rocks, you break right across the grains themselves rather than separating the grain boundaries. Geologists recognize three major groups of rock, and they differ by the processes by which they're formed. So this classification of rocks, this is a genetic classification based on how the rocks actually form. The first of these three great classes is called igneous rocks, and that includes all the rocks that form from a hot, molten state. Geologists make a further subdivision between volcanic rocks, those are rocks that solidify on the surface, and intrusive rocks that solidify underground. And there's really no difference compositionally between these two. It's just that one forms on the surface, one forms underneath the surface. If you see igneous rocks that cool very quickly, they're likely to be very fine-grained. For example, basalt. A basalt from Hawaii is a very fine-grained rock. You'll also see that because of all the gas that's contained in the rock, you often see lots of little air pockets and channels where the gas is expanded, puffing out the rock and making it porous. But if a rock cools very quickly, you might even get a volcanic glass, like the material called obsidian. And you may have seen pictures of this vitreous black glass material. So important was obsidian because of its sharp edge when it breaks, that it was used by Native Americans for its most efficient tools, for weapons. And indeed, all over the North American continent, you can find various pieces of obsidian spear points and other sort of tools that were made out of the very distinctive obsidian that comes from Yellowstone Park. This indicates there must have been a vast Native American trading route in obsidian because of the value of this volcanic material. Now, intrusive rocks, as I said, have basically the same composition as basalts and obsidian, but they cool much slower, and so they have much larger crystals. So once again, for example, if you look at a Pikes Peak granite, or any granite for that matter, you'll see individual crystals. That implies that the rock cooled slowly enough for those crystals to form. The second great class of rocks are called sedimentary rocks. And these are rocks that are deposited in layers. They can be either deposited as layers of particles, as in layers of sand or layers of silt and mud, or they can be chemical precipitates. And some sedimentary rocks, for example, are salt deposits, layers of salt that evaporated out, or maybe layers of calcium carbonate called limestone. We have sandstone. Those are sedimentary rocks formed from sand. It can accumulate at ocean margins, at beaches, for example. Sandstone can also accumulate in deserts. Shales are formed from mud and silt, layers of very fine particles. And very often you'll find thick deposits of shale that come from old ocean basins, where thousands of feet of shale may have been deposited over millions of years. Limestones. Limestones are formed from the gradual buildup of calcium carbonate, sometimes just by dead animals, shellfish, falling down and forming layers of shells in the bottom of the ocean, sometimes by the gradual buildup from chemical precipitation of calcium carbonate. Now, a very common feature of sedimentary rocks is that they hold fossils, the evidence of past life. I'm going to talk a lot more about fossils in Lecture 56, but suffice it to say that fossils provide invaluable information about the evolution of life, the development of life over millions of years of Earth history. An important idea in sedimentary rocks is what's called the law of superposition. It's a fairly obvious idea that the younger layers are always deposited on top of the older layers. If you go to Midwest road cuts, for example, you'll see flat-lying sedimentary rocks in the road cuts, and you know that the layers on top are always younger than the ones on bottom. And this is very important, again, in understanding the evolution of life, because as you look at layer after layer after layer, you see that the life forms change. And when life forms change, that is evolution. Okay, third, we come to metamorphic rocks. And metamorphic rocks include all the rocks whose mineralogy is altered by temperature and pressure, sort of like in a pressure cooker. Now, in an earlier lecture, we learned about phase transitions, such as that transition of graphite to diamond under temperature and pressure. That occurs deep within the Earth. And most other minerals, if they're subjected to high enough temperature and pressure, they too will transform. They will change their form. And so you get, as you take a sediment and bury it deeper and deeper and deeper, it will go through a series of transformations called metamorphism. There are wonderful sequences of metamorphic rocks as you go from flat-lying sediments to more and more deeply buried materials that have then been uplifted and exposed. You can see this in New England, for example. You can start with a nice mudstone or shale, and after it's been baked and pressurized and cooked, it eventually turns into a slate, a hard slate that can be used, for example, for roofing materials or for flagstones in your garden. And then if you take a slate and you squeeze it and heat it more, eventually those minerals will transform largely to micas, and you'll form a schist. And you may have seen in New England or other parts of the country the shiny mica surfaces reflecting the sunlight as you drive by outcrops of this metamorphic rock. And then you subject a schist to higher and higher temperatures and pressures, and eventually can transform to the layered gneiss, where you still see some of those sparkling minerals, but this is a denser, harder rock of different minerals, higher pressure and higher temperature minerals. And so step by step, you go up the metamorphic ladder of temperature and pressure. You may also, often in New England and in other parts of the country, find marbles. This is a limestone that has been recrystallized by the effects of temperature and pressure, and all marbles began as limestone in this way. So we have our three basic rock types. We have igneous rocks formed from molten material. We have sedimentary rocks formed in layers. And finally, metamorphic rocks formed by the transforming influence of temperature and pressure. Now, let's talk about the early Earth. Think about what the Earth was like right during the period of the Great Bombardment, the final stage. The Earth had been formed, but it was still subjected to an incessant rain of asteroids and comets hitting the surface, forming huge, great fountains and flashes of fountaining rock, of magma. There were volcanoes all over the surface of the Earth. The Earth was largely molten. Gradually, however, that incessant bombardment had to subside. The Earth had to cool. The volcanism must have slowed down. And eventually, on certain parts of the Earth's surface, the first black crust of rock formed. And what were those first rocks? Well, of course, they were igneous rocks because they all formed from the molten state. So we know that the Earth's first rocks must have been igneous. Now, there was still a lot of intense volcanic activity. More and more volcanic rocks were being poured onto the surface. But many of these volcanoes also released into the atmosphere the various gases that made up the early atmosphere: water vapor, nitrogen, CO2, etc. And so you formed the first clouds and the first rain. And after the first rain came the first erosion, the first freezing and thawing, perhaps even in the polar regions eventually. You began to break up the igneous rock into small fragments, into small particles. And when you did that, you began forming the first layers of sediment. And as you accumulated layer upon layer of sediment, you could then form the first sedimentary rocks. I imagine sandy beaches, probably of black grains, because that early basalt must have been very, very black. And you can imagine them forming sandy, black beaches along the shores of the earliest oceans. Maybe those were the first sediments. Maybe they formed the first sedimentary rocks. But in any case, those rocks had to form. And so you had igneous rocks and you had sedimentary rocks. And then you know the plate tectonic processes must have been very rapid in those early years of the Earth. They must have been faster than today. And so igneous rocks and sedimentary rocks were subducted down. You buried things. You had tectonic activity. And so both igneous rocks and sedimentary rocks were transformed by metamorphism. And metamorphic rocks were also being formed in the Earth's interior by temperature and by pressure. Sometimes the sediments would be metamorphosed just by the heat of an adjacent igneous intrusion. You had a new mass of magma coming up through the crust. If it intersected a sedimentary rock, that sedimentary rock would be baked and altered just by the heat. Well, today that cycle continues. We still have the formation of igneous rocks, of sedimentary rocks, of metamorphic rocks continuing all over the Earth. And it's the material that forms these rocks is constantly recycling from one type to another. Imagine a silicon-oxygen bond, that strong bond that lasts for a long time. You can imagine the silicon-oxygen bond that occurs in a grain of sand at the beach may have undergone many, many rock cycles, going from igneous to sedimentary to metamorphic and back over and over and over again. The same atoms used again and again. And they continue to cycle and will continue to cycle for billions of years more. Well, how do geologists deduce the history of a rock? How can you do this? How can you look at a rock and say what happened millions or even billions of years ago? It's geology. Geology is the science of rocks, and first and foremost, it's a field science. Our data is collected in the field. When geologists go into the field, they make observations, they make measurements on the rocks themselves. They measure, for example, the relative positions and the thicknesses of different rock formations. They identify the rock types. They say, is this a marine rock formed in an ocean environment? Is it a land rock? Is it igneous? Was it formed in a volcano or in a metamorphic event? You identify the rock type, and that tells you a great deal right there about the history of that outcrop. You map folds and faults in the rock. You look for places where younger sediments lie on top of older sediments. You collect the fossils. You see where younger intrusives of molten rock cut across older formations. That's another kind of relationship of age, because a younger rock has to cut across the older rock. You also collect lots of samples, hundreds of pounds of samples. I know, I've been there. I've hiked down the mountains with 50 or 60 or 80 pounds on my back of rocks. You carry them back to the laboratories and you keep analyzing them there. You can measure their ages using radiometric techniques. You can make thin sections of the rock and look at the minerals and the relationship of the minerals and learn much about the history that way as well. And history is the key here. Most of all, geologists think about history. Every outcrop, every road cut has an ancient history. Geologists use subtle clues to deduce these histories. It's sad in a way that because the Earth keeps recycling its rocks through plate tectonics, most of the history is absolutely lost forever. The oldest oceanic rocks, the oldest oceanic crust is only about 200 million years old. All the rest of the oceanic crust has been subducted. Now, continental material can be much, much older because the continents, remember, float on top of the plates, sort of permanently floating around on top of the plates. Nevertheless, there are very few rocks that are older than about 2 billion years, and that's less than half of the Earth's total age. In fact, there are only a handful of outcrops older than about 3 billion years, the oldest known rocks from Australia being about 3.8 billion years old. Thus, we know almost nothing about the geology for the first half of its existence. On the other hand, thanks to the abundance of accessible rock formations, and especially fossils, we know a great deal about the last billion years of Earth history, and we can document that extremely well. As you drive past road cuts or route outcroppings anywhere in the world, the rocks have amazing stories to tell. And I want to tell you 3 stories about 3 of my favorite outcrops. I'm going to begin by telling you about a beautiful rock, a fossil-rich rock from Cincinnati, Ohio. Cincinnati is a vast storehouse of fossils from the Ordovician period. Virtually any road cut, any place you stop in the Cincinnati area, you pull off the side of the road, you go and look at the rocks, and you'll find abundant, beautiful fossils. And these fossils are beautiful not only because they're varied, because they're large and so forth, but also because of a very particular kind of fossilization called silicification. The Cincinnati fossils were replaced, the original calcium carbonate shells were replaced by silica, which is tough and hard. And so these fossils are preserved in exquisite detail and beauty. There are hundreds and hundreds of different species in the Cincinnati area, so it's a rich treasure ground for fossil hunters, for professional paleontologists alike. So I want you to imagine the Cincinnati area about 500 million years ago, when Cincinnati was under a shallow sea. It was an inland sea that covered, in fact, much of North America. And there was a great coral reef system. That coral reef system teemed with life and deposited thick layers of limestone. It probably was very similar to the Great Barrier Reef is today, depositing layer after layer of limestone, and numerous other shells and organisms died and fell down and helped build up these layers of fossiliferous rock. Now, gradually, for another 150 million years, the reefs were buried. The inland sea of North America was filled with many thousands of feet of sediments, and these sediments occur throughout the Midwest. That's what you see when you drive through the Midwest. By 350 million years ago, the basin was much, much shallower than it is right now, and land sediments started to fill in that basin. That includes things like coal layers. Coal layers represent swampland. So far above the Cincinnati Ordovician layers that we're talking about, layers upon layers upon layers in other parts of the Midwest, including the great coal beds that are now mined in Pennsylvania and other parts of the United States. By 200 million years ago, there were great tectonic forces that gradually arched North America and started bending it upward. Now imagine how this happens. You have a thick layer of sediments, which has been deeply buried, but then other forces come into play and start uplifting those layers of sediment. So gradually, as the layers of sediment are lifted up, streams and rivers cut through that, cut more deeply. Erosion takes place, and layers are stripped off. And at the highest point of that arching, you have the greatest erosion, and that was right near Cincinnati. So Cincinnati is where the oldest rocks, the most deeply buried rocks, come closest to the surface. You have the help of things like the Ohio River that cut down deeply through these rocks and exposes more and more of them each year. So now we see these ancient rocks, the ancient coral reef exposed at the surface, which was buried 500 million years ago. Well, I have another fossil-rich rock I want to tell you about. This one comes from the foothills of the Appalachians in West Virginia. Now, I've got to give you the picture of how I found this. We were driving along, my wife and I, through the Appalachian foothills of West Virginia, and there's a very steep outcrop. It's actually a pretty lousy rock. It was a very thin and what's called a fissile shale, a mudstone that was deposited some 400 million years ago. If you take a piece of this shale in your hands, it just breaks apart so easily. And this is what this so-called rock outcrop was made of. But if you look extremely carefully at these rocks, if you focus in on the tiniest detail, once in a while, you could find an absolutely exquisite tiny fossil, a fossil of a marine organism, shellfish called brachiopods and trilobites, fossils that gave incontrovertible evidence these shales were once deep ocean deposits, deposited layer upon layer upon layer, perhaps thousands of feet thick of these shales. Now, the thing that was really odd about these shales is not only were they high on the side of a mountain road cut, but the layers of rock were vertical. They were all standing on end. And you could see the layers of sedimentary rock not lying flat as they must have originally been, but somehow tilted up on end. How in the world could that have happened? Well, let's look at the history of this rock. First of all, as I said, the rock is a shale. That means it was deposited once upon a time as a very fine-grained mud in a sea, in an ocean. The fossil specimens are diagnostic of a marine environment, that it must have been a saltwater environment, an ocean, bay, or inlet about 400 million years ago. We also know from looking at other outcrops that there are thousands upon thousands of feet of sediments that collected in this sea. And looking at nearby sections of Virginia and West Virginia, you can see that the sea was bounded to the west by a very mountainous continent with the young Appalachians. And it was bounded to the east by a series of volcanic islands. So this was very much like the Sea of Japan today, where you have China to the west and the islands of Japan to the east. And the sea between them is sort of the environment where these fossils must have been living. Now, the ancestral Atlantic Ocean extended much farther to the east, and it was slowly closing at that time. So this was an earlier stage of the Atlantic Ocean where the Atlantic was just starting to close up. About 250 million years ago, continued plate motions closed up the ancestral Atlantic Ocean for good, and also caused northern Africa to plow into North America. So the fossil-bearing sediments that were deposited in these layers upon layers were crumpled up, they were tightly folded, and they were thrust up onto the flanks of the Appalachian Mountains, just sort of like squeezing and folding and crumpling up the layers. And some of those layers became vertical at that point. At that time, the Appalachian Mountains were the tallest mountain range in the world, and these sediments, which I'm describing to you, would form part of the foothills of that Appalachian mountain range. And then, as we noticed a couple of lectures ago, about 200 million years ago, North America and Africa began to separate again. They opened up the modern Atlantic Ocean gradually, and the Appalachians began to erode. Well, today the Appalachians are almost worn away, but there are enough rocks remaining, fossiliferous rocks and other rocks from the core of the Appalachians, to tell that amazing story. Let me tell you about one more specimen. Those of you who have been to New England may have seen some of the great marble quarries that you can find in New Hampshire and Vermont. And I have a specimen of Vermont marble a specimen of limestone that has been baked and cooked and altered. So now you see the individual crystal facets of the recrystallized limestone. You know that marbles are beautiful rocks. You can cut them, you can polish them, use them as ornamental stones, and they have beautiful patterns and swirls and lines. Some of them are brightly colored, some of them are pure white, used for statuary. That's the distinctive characteristic of marble. But all marbles, you might be surprised to know, began as limestone. They began, for example, as coral reefs, areas that were teeming with life in a deep ocean. And this theme that we've seen, rocks that are deposited as flat layers, as sediments in an ocean, can often be transformed. In this case, in the case of Vermont, the rock began as a coral reef in an age similar to those Cincinnati Ordovician rocks. It formed as countless tiny organisms living as the coral built up layer by layer of the calcium carbonate that would become the limestone. Now, over the ages, these marine sediments were buried deeper and deeper and deeper, crushed, in some cases perhaps as deep as 20 or 30 kilometers beneath the surface. Think of that, 30 kilometers straight down. And there they were altered by temperature and by pressure. They were transformed into marble, a metamorphic rock. The composition of these rocks did not change. They were still calcium carbonate. Indeed, the same calcium carbonate that made up the tiny organisms of the coral reef. And yet over geological time, through deep burial, through baking, through squeezing, in the pressure cooker of the earth, you can transform these rocks, these minerals, in dramatic ways and form the thick deposits of marble. Now those marble deposits have come to the surface, and we see once again how humans can transform and change the cycle. When we see high-quality marble come to the surface, we don't just let it sit there. We go out and quarry it. And we transform those marble into monuments, into our gravestones, those, quote, eternal and lasting markers of our lives. But the gravestones of marble also are destined to erode away, to gradually return their atoms back to the earth, where they will cycle again and again and again for billions of years in the exact same rock cycle that we're talking about. In summary, let me remind you of the three great classes of rocks that make up the rock cycle. We have igneous rocks, rocks that are formed in the molten state, that pour out on the Earth's surface from volcanoes as volcanic rocks, or are intruded deep in the earth to form intrusive rocks. Igneous rocks can be very fine-grained when they cool rapidly at the surface. Igneous rocks can be quite coarse-grained if they cool deep underground, as in a body of granite. We also have seen sedimentary rocks, rocks formed of layer after layer of sediments. These sediments can be deposited as small particles, sand grains, silt grains, perhaps mud, or they can be chemical precipitates, calcium carbonate, or maybe salt, forming layer after layer of sedimentary rocks. And then we have metamorphic rocks, rocks that are transformed by temperature and pressure. You can start with an igneous rock and make a metamorphic rock. You can start with a sedimentary rock and make a metamorphic rock, or indeed you can metamorphose metamorphic rocks themselves. And indeed, each of the three rock types can be transformed into the other two through the processes of the rock cycle. Every rock, every specimen, every outcrop has a rich and ancient history. Every rock has an amazing story to tell. The science of geology allows us to read that story. You've probably noticed throughout this lecture, throughout all the lectures on geology, the recurrent theme of the abundance of life on Earth. It's now time to turn our focus to living things, which are the most complex systems on Earth.